Okay, let me go ahead and get started. So today I want to talk about variable selection for predictive models and look at several methods for doing this. I won't look at every possible method for doing this, but some of, I think, maybe the more interesting ones. I'm going to first look at sort of the older method of forward and backward selection when we do ordinary least squares regression. Then I want to talk about classification and regression trees. And then similar to that, we'll look at random forests and boosted trees. I won't say too much about boosted trees because it's essentially the same as random forest. And then we'll talk about more multivariable adaptive regression splines, or MARS. And then I want to end up talking about penalized regression, which we've talked about before, but I want to go into a little more detail on it. So the regression models that we want to develop, the typical multiple linear regression or logistic regression, and then survival analysis, where we have, in all three cases, similar regression equations. That is, we have predictor variables and then a regression coefficient for each variable. And so in multiple linear regression, our outcome is a continuous variable, hopefully more or less normally distributed, although that assumption can be violated to a fairly large degree, and we'll still be okay. And then binary logistic regression, where we have a dichotomous outcome, and we look at the probability of an event. And then survival analysis, where we're looking at survival to a particular time point. So I want to start out looking at the selection methods that are common and used in the past. So I want to start out with one that was fairly common. Every once in a while, I'll still see it. And that's you do a univariate analysis on all your predictor variables and then choose the ones that are statistically significant for a multivariable analysis. That's a bad idea. And you don't want to do that. And the reason is that if you leave out a variable that's not statistically significant in univariate analysis, it's very possible that variable could be an important predictor, even if it's not statistically significant in the full model. So that's, as I mentioned, something you don't want to do. The other common method, and that's built into most statistical packages, is forward selection or backward elimination, or it's a combination of the two. Here you select an alpha rate for your selection variables and out for your elimination. And so that's just setting an alpha error rate, could be 0.05. A lot of times investigators use 0.1 or even sometimes 0.2, depending on the context. But basically what you're doing is you're selecting a variable to put in if the p-value for that variable is 0.05 or less, or if you're doing backward elimination, then if it's greater than 0.05, you take it out of the prediction equation. So I want to illustrate that and give you some of the kind of pros and cons or ins and outs of doing that. So in this application, I want to look at a screening test for diabetes or impaired glucose tolerance. And so the standard for diagnosing diabetes is the 2-hour oral glucose tolerance test. And so what we want to do is we want to see if a more convenient and less expensive test, a 1-hour capillary glucose test, basically a finger stick, how well does it do in predicting diabetes? And then we want to see if age, gender, race, and BMI add to the accuracy of the capillary glucose test in predicting diabetes or IGT. And so this is what our data would look like. We have age, race, sex, BMI, and then the 2 glucose tests are continuous variables, but we're going to do a couple of different tests here where we're going to dichotomize the the 2-hour test. Typically, or at least in the past, it was 140 or greater was an indication of diabetes. So that's going to be our outcome variable. Obviously, the other ones, race and gender, are going to be what we call dummy coded. That is 1 for African Americans, 0 for Caucasians, and 1 for female, 0 if it's male. So our predictive model is IGT as a function of our capillary glucose test plus age plus gender plus race plus BMI. And you noticed in this formulation here, this model, we've not included any interactions, which we'll look at later that we might want to do. But anyway, so we're going to do backward elimination. Here we're going to start with all risk factors in the model, and then we'll eliminate the least predictive risk factor, and then we'll compare the reduced model with the full model. If there's no statistical significance when we do this comparison, then the reduced model is it's better in the sense that it's more parsimonious. It's a smaller model, but it predicts just as well as the larger model. On the other hand, if it turns out that there's a statistically significant difference between the reduced model and the full model, then we have to go with the larger model because whatever we've taken out is an important predictor. So here's our logistic regression results. And so you can see that the 1-hour test, age in 10-year increments, African American, female, and BMI. So you can see that they're all statistically significant at the 0.05 level, except for African American or race. And so if we're doing backward elimination, that's our first candidate for taking it out of the model. And so then we would rerun the analysis with just the 4 variables in it, the capillary GCT, age, female, and BMI, and see what we get. And so if there's one of these turns out to be not statistically significant, then we would take that one out and compare it to the larger model, and so forth until we got down to the point where we couldn't eliminate any other variables. However, as it turns out, if we eliminate all the variables except for the capillary test, the odds ratio turns out to be 1.39. If we have all the other variables in the model, the odds ratio is essentially 1.37 or 1.38. So in terms of the variables, the risk factors that we have in our model, it looks like we could take all of them out and we would still get just as good a prediction as we would with just the capillary glucose test. And you can see that the confidence intervals are pretty similar for the adjusted one and for the unadjusted one. So that's sometimes it's if we did forward selection, if we do it that way, then we would add one variable at a time and see if it changes our results significantly. Or in this case, whether it's statistically significant or not, we can see that the odds ratios here are really similar. So it's probably telling us that it's not really worth it to do a larger model. Okay, so the next method is classification and regression trees. And so this is actually a pretty interesting and I think in certain contexts a really useful way of doing models is creating trees. And so basically what this is taking particular outcome, and it can be continuous or dichotomous. And what we're going to do is we're going to do binary splits of variables that result in homogeneous subgroups. Our variables that we have in the model can be either continuous or categorical. And also positive about this particular method is that you can include missing variables without having to exclude them or do anything, impute them or whatever, because what tree regression will do is it will make missing values a separate category and include those in the tree. And so this is what a tree looks like. It's actually upside down. So we start with the root that has our outcome. And so in this case, whatever our outcome is here, 40% of the patients experience that outcome. And so our first split here is by age. And so it splits at age 65. And so you can see that if they're less than 65, the percent of those that have the outcome is 17%, compared with those over age 65, where 75% of our patients experience the outcome. And then we may or may not have a further extension of the tree, or talk about, use the terminology, growing our tree. And so if the patients who are less than 65, which are 60 of them, then there's another split by sex. And so in this case, 7% of the 60 have the outcome versus 27% for males. And when there's no more splitting of the trees, then we call that a terminal node. But this is what our tree is essentially going to look like. And so we can put any number of trees or any number of variables in our regression equation. And so basically what the model or what the regression trees are going to do is it's going to create branches which are optimal splits of risk factors. And the first one is going to be the most important risk factor. In other words, it's the variable that gives you the largest difference between our subgroups, or make subgroups that are as different as possible between those that experience the outcome. And so when we grow our tree, we can set a minimum number of patients to be in a node or in a split. I think most software uses 5. That might be too few for my thinking, but maybe 10 would be better. But anyway, you can set that in the however few numbers of patients you want in a node. And then we can grow the tree as big as it will go, down to the number of patients we've set for a particular node, but then it might be reasonable to prune the tree. Obviously, what you do with the tree is prune it. Then there's ways of determining, just like there was in backward and forward selection, what is a reasonable sized tree, or what's the smallest tree that you can have and still predict, as well as with the larger tree. So I'm not going to go into the specifics of actually doing that, but what I want to do is look at a tree model of in-hospital mortality. And so in this application, we have 28 risk factors. These are patients who are undergoing PCI, percutaneous coronary intervention. And so of these 28, 3 of them, age, ejection fraction, and BMI, are continuous variables. All the rest are categorical. Most of them dichotomous, variables. So when we do the tree analysis with these 28 risk factors, this is what we get. This is what our tree looks like. And this has been pruned back to the most parsimonious. So we start out in hospital mortality, and we've got like 35,000, patients. So 5.5% of them experience in-hospital mortality. And the primary variable predicting this is shock during PCI or not. And so you can see that for those who experience shock during the procedure, 29% die or in hospital, whereas only 2.7% of those not experiencing shock die in hospital. And so from there, then you can see that our branches split with different variables. So those that experience shock, we have another split of ejection fraction. And so we can see that those who have ejection fraction less than 40% or missing, that's what NA, that of those remaining 34% experience in-hospital mortality, whereas those greater than 40 only a little less than 15%. And then for those not experiencing shock, but still expire in hospital, the next division in the tree is age, and age in this case splits at 71. So those greater than 71 years of age, 6.9 die in hospital, whereas those less than 71, only 1.5% die. Now, there's some interesting things, and then it, keep growing the tree till we deem or find out that it's the best prediction that we can get with the number of nodes that we have. You notice a couple things here. Ejection fraction shows up in all of the or in the splits here, and it's always splitting at 40%, regardless of where it's at in the tree. On the other hand, if you look at age, age has different values for splitting. So with the no shock people, it splits at 71. For those who experience shock and have an ejection fraction greater than 40%, it splits at 65, and those that have no renal failure at 58. So what this does is this tells us, it gives us an idea of the potential interactions between our predictor variables. So we see that shock is our most important one, then ejection fraction, then we have renal failure, yes or no. And so you can see that for those who are in experience shock have an ejection fraction less than 40%, and also have renal failure, that their death rate is over 61%, compared to those with no renal failure, where it's 31%. And then if the patient doesn't have renal failure, then we have another split at age 58. So this gives us not only an idea of what variables are important and which one is most important, but it also gives us an idea of which variables are related to one another. And so we would primarily be interested in those experiencing shock and what other variables might enter into predicting shock. Okay, so that's just growing a single tree. And so the downside of doing a regression tree is that it's going to apply to your data. If you try and use the same variable splits for somebody else's data from a similar the same population, but just a different sample, you're probably not going to do very well. So the next method we want to talk about is random forest. And I just mentioned boosted tree here because random forest is the idea of growing a large number of large trees. We're then going to bootstrap those trees with replacement. Boosted regression is similar to that, except we grow a large number of small trees, or smaller than random forest trees, but otherwise it's a similar method. So we'll do random forest here. So basically what you do is you sample, you grow a tree, a large number of trees, and then you sample with replacement. And so when you do that, and this is true anytime you bootstrap with replacement, you use about 2/3 of the sample. And so that means about 1/3 is not used in the tree model. So you grow a very large tree with bootstrap sample. This is referred to as bagging. And then when you have 1/3 of the sample left over that was not used in the development of the tree, you run the remaining 1/3 of the sample down the tree, and it's referred to as your out of bag test sample. So you're growing a tree by bootstrap with replacement, and then you're testing whether that how well that tree is doing using the remaining 1/3 of your sample. So then that at each node of the tree, random forest then randomly selects some of the risk factors, and so the square root of the number of risk factors is usually what it selects. And so you then have your nodes split based only on the selected factors. And then when you get to the next node, you randomly select another set of risk factors, and so on as you're growing the tree. And so you repeat this process for a couple hundred trees, and then you take or compute the accuracy for each tree, and you combine across all trees to get the best prediction model. So random forest is sort of a neat way of getting not necessarily a model in the same way that you get with multivariable regression, but it gives you an idea. Well, it tells you which variables are most important. And so this is one way that some software presents the variable selection, and it actually gives you the list of all the variables in the application I did here. I just picked out a few. And so it lists the variables in order of importance. And so all the variables to the right of the vertical line here would be the important variables, or would be statistically significant. if they're on the other side, the left side of the vertical line, then they're not so important. So here you can see that we have, and I forget what we're predicting here, but we have age, cancer, yes or no, and then the oxygen level would be the three most important predictors in our model. Sometimes you'll see this done as a bar graph rather than plotted this way, but basically that's one of the really great things about random forest, is giving you variable importance. The problem with random forest, though, is that to get the best model, what is done is you create an n-by-n matrix of proximities. That is, how many times pairs of cases end up in the same tree node. N, however, is the number of patients, not the number of risk factors. So if you have a very large database, this n-by-n matrix gets out of hand. So if you have like 35,000 in your database, then you get over 1 billion cells to deal with. And you can see that if the database gets really large, which that's not unlike a lot of databases that you might want to do data mining. But if that's the case, if there's a large number of patients, then random forest is not the method you want to use. What it is useful for is if you have a large number of risk factors in a few patients. And so in contrast to least squares regression, you can have more risk factors than you can patients. And so probably one of the primary examples of this is in genetics, where you might have a really large number of variables. So for example, like gene expression, you could have hundreds or even thousands of variables in just a small number of patients. And so that's a situation in which random forest is really good to use. Okay, so the next one I want to talk about is what's referred to as multivariate adaptive regression splines. And this is also kind of a really neat method, although it has its drawbacks as well. But it's non-parametric. In other words, we're making no assumptions about the distribution of any of the variables. The neat thing about it is that it takes into account higher order interactions. And in fact, it will look at all possible interactions in your data. And it's, it does this without, much input, without hardly any input other than your variables. It's fast. And what it does is it generates basis functions. And basis functions are essentially piecewise regressions. And I'll show an example of that in a minute. But basically, then what it does is it prunes the functions by backward elimination. In other words, it will generate a large number, or maybe all possible basis functions, and eliminate them in terms of their importance in predicting. So an example here, I want to develop a predictive model of obesity. And I'm going to do it two different ways. I'm going to analyze obesity as continuous and then dichotomous. And when I do it as a dichotomous variable, we'll dichotomize it at 30, a BMI of 30, which is the sort of the cutoff for being obese, less than 30 or over 30. And so what I want to use this or do with this is also illustrate the model complexity that may or may not include interactions. So here's a study with about 3,000, a little over 3,000 patients, and we have 5 predictor variables of obesity: age, gender, race, smoking or not, and then months since their last visit to their primary care physician. And you can see that the months since the last visit is skewed, probably is right skewed. The standard deviation is larger than the mean. But these are it's just with 5 variables, and we can use any number of variables that we might have. We can use a large number of variables in this case, but to show what the difference is here with just least squares regression is just the complexity. So in our analysis, if we do multivariable logistic regression or linear regression, we have BMI as a function of age, gender, race, smoking, and months since the last visit. When we do MARS, you notice it's the same kind of setup, except rather than having an additive model, we have a multiplicative model where we're going to look at the interactions between all 5 variables. As I mentioned, we're going to do this BMI as continuous and then BMI as with the cutoff of 30. And what MARS is going to do is give us a classification matrix. So in terms of the analysis, if we want to do linear regression with the interactions, this is what we would have to, if we wanted to put in all possible interactions, we would have to have a model with 29 terms in it. We would have the main effects, all the 2-way interactions, all of the 3-way interactions, the 4-way interactions, and then finally 1 5-way interactions. Well, obviously, in doing linear regression, you're not going to be able to put all those interactions in the model. And in fact, when you do just regular linear regression, once you get past 2-way interactions, and even just a few of those, it would get impossible to interpret. So these are the results from the multiple linear regression, where we're looking at BMI as a continuous variable. And so you can see that all 5 of our predictor variables are statistically significant. If we're looking at just the p-value for each predictor in the model. And so this is our analysis of variance table. Our overall model is statistically significant, but it turns out that for this model with those 5 predictors, that our model R squared. Remember now that we're looking at BMI as a continuous variable, so our statistic that we're really interested in here is our R squared, the percent of variance accounted for by the in the outcome that's accounted for by the predictors in the model. And you can see that basically it's just 6%. So even though we have a statistically significant model, our prediction is not real great. In fact, any model that you have that has less than 10% variance explained is not probably worth looking at. So what we want to see, does the MARS do any better? So you also with MARS get a list of the variable importance, and in this case it scales the variables in from 0 to 100 is a percent importance. And so you can see that being a smoker here is our top variable as far as prediction, then age, months since last visit, and then something of a drop off there. But if you have a lot of variables in the model, it'll list all of them and the importance down to something close to 0 for the least important one. And so here's our result from our MARS analysis. And so you can see that what we get here are basis functions. And you can see that our first basis function, and this is pruned because you can see that some of the basis functions are now left out. So it's pruned it down to the minimum number that gives the best prediction. And so we start out, our first basis function was indeed the smokers. And so the way that the basis function is labeled here is the maximum of being a smoker or not. And so it's either 0 if it's a non-smoker. If they're a smoker, it's basically 1 plus a very small number. And then you would multiply that by its regression coefficient over here. And so what you see is that for the dichotomous variables, there's only one basis function. So here we have smoker, here's for females, here's for African Americans. For the continuous variables, we can have more than one. And so you see that for more than one basis function so you can see that for the months since the last visit, it's going to be either that value minus 1.22, or if it's smaller, 1.22 minus whatever the value is for months since last visit. And if it's you can see it's the same thing. If it's greater, if it's less than for basis function 2, then it's going to be 0. So that's going to drop out. And then for age, you see that you get several different cutoffs here: 54, 70, 57, and 24 for basis functions. So what does this look like if you look at it in terms of piecewise functions? This is what it would look like. So for dichotomous variables, you get just the straight, this just goes from 0 to 1. So you always get a straight line for those. But you can see for our continuous variables, age and months since last visit, we get a nonlinear functions. And so that's another thing about Mars, is that it will, the predictor variables that are continuous aren't necessarily linear. And so you get different, that's why you get different cutoffs for the continuous variables. So the results here, we do our analysis of variance table. We see we have a statistically significant model, but look at the R squared. Now we've improved it from 0.06, but it's only improved to 0.08. So this really illustrates that even though our Mars model might be better, it's not really any better in terms of prediction than our least squares model in terms of the R squared. And so what this tells us is that whatever are good predictors of being overweight, we don't have them in our database, even though they're statistically significant. And so these would be our prediction equations for the continuous variable, or BMI is continuous. And then we would have for Mars, we would have for the linear regression, they'd be just like they typically are. You have your regression coefficient times whatever the value of the variable is. For Mars, though, we have our regression coefficients times the basis function. And so in this case, what I've shown is that either one isn't really a really great predictor of BMI. So then the other thing I did was to do a logistic regression where I've dichotomized BMI at 30. And so again, you can see that we have statistically significant p-values for the 5 predictor variables and their odds ratio. However, when we go to do our classification table of obesity, defined as greater than 30 BMI units, then this model classifies everybody as obese. And our area under the curve, our C index, is only 0.67, so this is not very good with the dichotomous definition of BMI, or being overweight. And so if we do the same thing in Mars, notice we have fewer basis functions, but we still have the same variables. And now if we do our classification matrix with Mars, using those variables, we get really great sensitivity. In other words, out of our 3,608 were actually obese. Our Moz model is saying that 6 has a sensitivity of nearly 1. On the other hand, its specificity is not so great, as is the positive predictive value. Is not real great. It has a really great negative predictive value. So even though our Mars classification is doing really great in terms of sensitivity, it's not doing so great in terms of positive predictive values. Using the model, we wouldn't be able to predict in another sample very well. Okay, so that's the Mars. Let me talk about penalized regression just for a little bit, because I've already talked about this in other presentations. In penalized regression, we have either ridge regression, least absolute shrinkage and selection operator, or the lasso, and then the elastic net, which is a combination of ridge and lasso. And essentially what penalized regression does is it shrinks regression coefficients towards 0. And so instead of making a decision based on p-values, you introduce a penalty that reduces the size of the regression coefficients and reduces them towards 0. So just to illustrate for those who are interested in the math of this, the penalties that are applied here. And so for the ridge regression, which is sometimes called the L2 norm, basically it's taking the regression coefficient and squaring it. And the lambda in there is what's called a tuning parameter, which is the case for all 3 models here. And so for ridge, in ridge regression, the regression coefficients are squared, so it's always going to be positive. And so is the lasso, but the lasso is the absolute value, not the square. And then the elastic net, which is the combination of both of them, you have this penalty here. The left-hand side of the equations here, you'll recognize that as just the residuals, the predicted minus the observed minus the predicted in your equations. So what it's doing is we're trying to minimize the error sum of squares. So I'll just, I've gone over this study before, so let me just kind of recap it here briefly in terms of predicting atrial fibrillation in patients, in our patients with hypertrophic cardiomyopathy. And so we have, I think it was 46 variables. And so here's a list of all the variables that we're going to, that we want to include as potential predictors of atrial fibrillation. And so you can see that doing least squares regression is going to be kind of minimal or kind of difficult to do here with so many predictors. So in terms of the sample, we have 96 total patients who had an AFib. Some of those had multiple AFibs, and then we had 2,500 and some that did not have AFib. And so of all these variables, we're going to see which ones are the most important ones in predicting AFib. So our outcome is dichotomous, just yes or no, but we're also looking at time to the event here. So it's basically going to, what we want to eventually get to is a survival equation of time to event. And so we're going to use the elastic net here, which is going to be something between ridge regression and the lasso. So one thing I forgot to mention is the lasso actually shrinks the coefficients to 0, which is sort of nice because then the decision is made for you. But of course, that's not always the best. There's some issues with the lasso as well. So the elastic net is becoming quite popular in doing regression when you have a lot of different variables. And as I mentioned before, when I went over this, we have like 10 data sets because we're doing multiple imputation for missing values. But I'm not going to go into that. Now, what I want to focus on is the variables and the importance from the elastic net analysis. And so out of the 10 data sets that we had, I listed all of the variables that showed up in any one of the data sets, any one of the 10 data sets. And so we came up with 17 out of the 46 that showed up at least once. But for our model, what we're going to do is take those that appeared in all 10 of the data sets. And so that turns out to be 11 variables that would give us our best model of atrial fibrillation. Now, the question is, so 11 is still quite a few. And so what we asked is, can we reduce the model further? And so what we did is taking those 11 variables and we did backward elimination. And we do that by looking at the likelihood or using the likelihood ratio test. And so when the likelihood ratio test is not statistically different, in other words, if the reduced model is not different from the larger model, then we can go with the reduced model. If it is statistically significant, then we can't reduce the model any further. So what we ended up with, and this is our table for the multiple, people had multiple endpoints. So we had a total of 127 AFib events. And so what we found was in using the 11 variables and then trying to reduce those further is that we had age, BMI, left atrial volume, contractile percent, mitral regurgitation grade 2 or 3. So we had those variables, and the reason that I have age broken up here into categories is because it turned out that in our survival model or our Cox model that the Cox model, the age rates, hazard rates were different depending on age. And so we broke them down into these categories. And so the way that we would look at this is in our overall model, our hazard ratios. So what this would mean that for every 5 units of increase in BMI, that you had a 40% increase in the odds of an AFib. And so on with the other ones, whereas contractile percent in 5% units was protective, what's called protective. That is, you had less odds of having an AFib event. And so in our statistics of how good our model did, we, of course, would compute the C index, or the area under the receiver operating curve, and then the calibration index. And so our C index for the overall model is pretty good. It's not great, but about 0.76. Our calibration index, that is how well the observed probabilities match the predicted probabilities, is really good. A calibration of index of 1 is perfect. So we did really well on our calibration index. And so these are the variables that the 5 variables that we came up with for predicting atrial fibrillation by using the elastic net. So I want to end up just talking a little about generalities of model development. And so basically, when you do model development, or when you want to fit a model, you are balancing bias and variance. In other words, as one goes up, the other goes down, and vice versa. And so I have examples here. When you overfit a model, you have high variance, is in the left-hand graph there. If you underfit, then you have high bias. And you can see that underfit models basically are incorrect models. And then what you want to get is strike a balance where you have low variance and low bias possible. So if you overfit your model, then it's probably only going to apply to the specific data on which it was developed. So if you take your model and try to apply it to somebody else's data, or to another data set from a sample of the same type of patients, it probably won't fit very well. So in sort of concluding here, just basically these data mining methods like elastic net or tree regression, and trees are probably, in my view, what I like to use them for is variable selection. And then what I get from that is I take those and then do sort of the if there's only a few variables left, to then do sort of the typical backward elimination and using the likelihood ratio test to determine our most parsimonious model, because you can get better prediction with a lot of variables in the model, but maybe that's not the best. Maybe that's not the best model in practical terms that would be useful in, say, a clinical setting. So if you, and one of the point I don't have here, but if you only have a few variables, like maybe 5 or less, then probably the regular forward-backward selection from doing least squares model or logistic models is not probably going to be too far off base. But if you have a lot of variables that you want to look at, then using some of these more recently developed methods is the thing to do. And then whatever model you come up with, you need to determine how well it's predicting And so like if you have continuous variables, it's the R-squared value that we want to look at in logistic regression, discrimination, and calibration. You need to determine how good your model is. As the statistician George Box once commented, all models are wrong. Some are just more useful than others. But that's a very important part of modeling, is looking at how well your model predicts. Okay, so I will stop there and have a few minutes here. If there are any questions, I think we use the question and answer for that. If there are no questions, or if you think of questions later on, please email them to me at my MedStar address here. So if there are no questions or comments, we will end there, and we will see you next month. So thank you for your participation.